Quantum fluctuations are transient energy changes that occur on very small scales of space and time due to the principles of quantum mechanics. These fluctuations arise because of the inherent uncertainty in quantum states, where energy levels can spontaneously change even in what appears to be a vacuum. Simply put, quantum fluctuations tell us that empty space is never truly empty. It is filled with virtual particles that appear and disappear, creating a dynamic and ever-changing quantum landscape. In the context of the creation of the universe, quantum fluctuations play a crucial role, especially in theories describing the early universe, such as the inflationary model. During the rapid expansion phase known as cosmic inflation, the universe grew exponentially, and quantum fluctuations that existed in the vacuum were able to stretch. As space expanded, these fluctuations in energy density could give rise to different regions of expansion, laying the foundations for the large-scale structure of the universe that we observe today, such as galaxies and galaxy clusters. Interestingly, some theories suggest that quantum fluctuations may also serve as mechanisms for creating entirely new universes. For example, in the multiverse scenario, it is hypothesized that a quantum fluctuation could give rise to a region of space with properties or constants different from those of our universe. This new region can be viewed as its own universe, fundamentally different from others due to the unique energy configurations created during the initial energy flicker. In essence, one can envision multiple universes, each defined by the particular properties of the quantum fluctuations that breathed life into them. In addition, the concept of a constantly fluctuating quantum vacuum may be consistent with a brane cosmology. When the brain moves in a higher dimensional space, it can interact with quantum fluctuations in that space, potentially leading to the creation of new universes or affecting the results of brain collisions. This interaction demonstrates how the principles of quantum mechanics can be deeply intertwined with the dynamics of cosmic creation, suggesting that the universe is far from a static entity and instead is rooted in the fluctuating nature of reality at the quantum level. Vacuum energy is a fascinating concept derived from the principles of quantum field theory, according to which even the emptiest regions of space are filled with residual energy. This energy is the result of quantum fluctuations, with virtual particles constantly appearing and disappearing. When we consider the implications of vacuum energy, it opens up critical possibilities for understanding both the very fabric of space in our universe and the potential nature of space beyond. In a cosmological context, vacuum energy is associated with a phenomenon known as dark energy, which appears to be the driving force behind the accelerated expansion of our universe. This energy creates a repulsive gravitational effect, pushing galaxies apart and influencing the overall dynamics of cosmic evolution. As scientists explore the nature of vacuum energy in our universe, questions are being raised about whether similar energetic conditions exist beyond our visible cosmos. If vacuum energy acts as a fundamental characteristic of all spacetime, it can significantly affect the structure and behavior of space beyond our universe. The concept of vacuum energy also contributes to understanding the multiverse scenario. In such a framework, different regions of spacetime, perhaps even entirely separate universes, may emerge as a result of changing vacuum energy conditions. Each of these regions may have different properties, particle types, and fundamental forces based on the unique characteristics of their vacuum energy. This means that a vast landscape of different universes may exist beyond our universe, each shaped by its vacuum state, resulting in a rich variety of realities. In addition, vacuum energy can be related to the idea of bubble universes, in which regions of space undergo phase transitions, leading to localized energy fluctuations. Such transitions can lead to the emergence of new universes as they are dramatically inflated, differentiating themselves from their surroundings. This suggests exciting dynamics in high-dimensional space, where vacuum energy properties can create the conditions necessary for the birth of new cosmic environments. As researchers continue to study the phenomenon of vacuum energy, our understanding of space and time is expanding beyond the limitations of our singular universe. The implications of this energy offer a broader perspective that challenges our understanding of existence itself, suggesting a complex tapestry of interwoven universes based on the unyielding presence of vacuum energy throughout the cosmos. Quantum foam is a concept that originated in the field of quantum mechanics, especially in the context of quantum gravity. It describes the idea that on extremely small scales, on the order of the Planck length, which is a tiny fraction of a meter, space-time can be far from smooth and continuous. Instead, the vacuum can be viewed as a frothy, ever-changing medium filled with constant fluctuations in energy. In this case, vacuum energy resembles a turbulent sea of virtual particles and fields. This phenomenon reflects the uncertainty inherent in quantum mechanics, where classical notions of distance and time break down. The implications of quantum foam are profound, especially when one considers the nature of space-time itself. This suggests that the vacuum of space is not simply empty, but rather is a living and dynamic entity that can influence the structure of the universe. These fluctuations can have significant consequences on larger scales of cosmic structures, potentially affecting the organization and evolution of matter. In terms of universe creation, quantum foam can serve as a potential catalyst for the emergence of new universes. In this chaotic sea of fluctuating energy, intense fluctuations can arise that lead to localized high-energy conditions. If these fluctuations reach a critical threshold, they could trigger a rapid expansion reminiscent of the Big Bang and thus form a new universe. This idea is consistent with some theories in cosmology where quantum processes play a crucial role in the genesis of universes. In addition, quantum foam may be related to the concept of a multiverse. Since different regions of quantum foam exhibit different energy configurations and fluctuations, each of them can give rise to distinct regions of spacetime with different physical properties. Consequently, this could lead to the creation of different universes, each governed by its own unique laws of physics and enriching the landscape of the multiverse. The study of quantum foam is forcing scientists to reconsider the dynamics of cosmic creation and the very nature of reality. By exploring how unpredictable behavior at the quantum level can culminate into large-scale cosmic phenomena, we gain a deeper understanding of the origin of the universe and the potential existence of an infinite number of universes formed by the fundamental building blocks of spacetime. Studying quantum fluctuations in the laboratory is a challenging but fascinating endeavor that requires advanced techniques and precise measurements. Scientists use a variety of techniques to observe these seemingly elusive phenomena, often using high-energy physics experiments, quantum optics, and condensed matter physics to investigate the quantum sphere. One known method involves the use of laser technology to manipulate and detect quantum states. For example, in experiments with ultra-cold atoms trapped in optical lattices, researchers can create conditions in which quantum fluctuations can be observed directly. When atoms are cooled to near absolute zero, particles behave according to quantum mechanics rather than classical physics, revealing fluctuations in their positions and momenta. Such a setup allows scientists to study how these fluctuations contribute to various quantum phenomena such as superfluidity and quantum coherence. Another approach involves the use of high-energy particle colliders such as the Large Hadron Collider. These facilities accelerate particles to speeds close to the speed of light, creating extreme conditions in which quantum effects become visible. By analyzing the results of high-energy collisions, scientists can indirectly observe quantum fluctuations and analyze how they affect the behavior of fundamental particles. This research has led to significant discoveries, including the confirmation of the existence of the Higgs boson and the study of supersymmetry, which are closely intertwined with quantum field theories. Quantum fluctuations also play an important role in experiments aimed at measuring the Casimir effect. This phenomenon arises from vacuum fluctuations in the electromagnetic fields between closely spaced conducting plates, creating a force of attraction due to the confinement of these fluctuations. By measuring this force with high precision, scientists gain insight into the nature of vacuum energy, quantum field theory, and the underlying structure of spacetime. Of profound significance are the discoveries gained from studying quantum fluctuations in the laboratory. Researchers have deepened their understanding of quantum mechanics, explored the foundations of quantum field theories, and even contributed to the development of new technologies, such as quantum computing and quantum cryptography. These experiments not only test the limits of existing theories, but also challenge our ideas about reality by revealing the complex interplay between vacuum fluctuations and the fundamental forces that govern the cosmos. As technology advances, the study of quantum fluctuations promises to reveal even more of the mysteries of the universe, deepening our understanding of both the micro and macro scales of existence. The zero-point energy field refers to the lowest possible energy state of a quantum system, even if the system is at absolute zero temperature. In this state, particles still have residual energy according to the principles of quantum mechanics, according to which even a vacuum is never truly empty. This concept assumes that there is a background energy throughout space that is interrupted by continuous fluctuations of fields and particles that arise spontaneously. Understanding the field of zero-point energy has profound implications for both our observable universe and the potential vastness beyond. One of the key features of zero-point energy is that it is ubiquitous. It permeates space regardless of whether particles or matter are present. This internal energy field serves as a background for all physical processes and can influence the dynamics of the universe on both small and large scales, providing a rich ground for the study of fundamental phenomena. By considering the implications of the existence of a zero-point energy field beyond our observable universe, we enter the realm of speculative cosmology and theories like the multiverse. If zero-point energy is a fundamental aspect of the fabric of existence, it is conceivable that it could allow for the creation of regions of space-time in regions beyond what we can currently detect. Different configurations of zero-point energy can give rise to universes with different physical properties governed by different fundamental forces or constants. This opens up the possibility of a multiverse, where each universe can function according to its own unique set of rules derived from zero-point energy fluctuations. Moreover, the zero-point energy field may also play a role in cosmic inflation. The energy associated with this field may have been crucial in the early moments of the universe, driving its rapid expansion. If this energy field persists beyond our observable universe, it may continue to influence the evolution of unobservable regions. These fields may have their own structures, similar to universes formed by the same fundamental principles that govern the behavior of our own cosmos. Studying the nature of the zero-point energy field is forcing scientists to rethink ideas about reality, time, and space. As scientists try to understand its role in the cosmos, profound questions are being raised about the interconnectedness of all things and the possibility of a vast, entangled multiverse sustained by the very energy that walks throughout the universe and beyond. Cosmic topology refers to the study of the large-scale structure and shape of the universe, investigating how its geometry and configuration can influence the general nature of cosmic phenomena. At its core, cosmic topology seeks to understand how the universe is connected and organized, encompassing ideas not only about its curvature, but also about its connectivity in higher dimensional spaces. The shape of the universe is a fundamental question of cosmology, which is heavily influenced by the general theory of relativity and the distribution of matter and energy within it. According to traditional views, the universe is often considered flat, closed, or open, depending on the curvature formed by gravitational forces. These geometric properties can significantly affect the history of the universe, its fate, and the paths light takes as it travels through it. For example, a flat universe expands forever at a constant rate, while a closed universe may eventually collapse in on itself. However, cosmic topology extends this discussion by considering how the universe can collapse or fold in on itself, creating a more complex structure. It is hypothesized that the universe may have a more complex shape, such as a torus or higher dimensional manifolds. In simplistic terms, this means that if you travel far enough in one direction, you will eventually return to your starting point, similar to walking across the surface of a donut. Understanding cosmic topology can have profound implications for our understanding of the universe, helping to shed light on questions about how we can observe distant galaxies and the cosmic microwave background radiation. According to some topological models, there may be specific patterns or irregularities based on the shape of the universe that scientists can measure and analyze to determine the basic configuration of the universe. Researchers are using sophisticated mathematical models, cosmic observational data, and gravitational wave measurements to further explore these topological questions. The results of these studies may change our understanding of cosmic evolution and interactions. Ultimately, cosmic topology not only helps us appreciate the scale of the universe, but also inspires us to explore the fundamental nature and interconnectedness of all things, including the very fabric of space-time itself. The shapes proposed for the universe are intriguing concepts that arise from research in cosmic topology and geometry. These shapes are intended to characterize the large-scale structure of the universe beyond the standard flat, open, or closed models typically explained by the general theory of relativity. Among the most interesting geometric shapes are the torus and the Mobius strip, each with unique properties that offer new insights into the cosmos. A donut-shaped torus is one possible topology of the universe. In this model, space can be connected in such a way that traveling in one direction can take you to your starting point after a long journey, giving the impression of a finite universe without boundaries. This configuration suggests that if two observers start from the same position facing the same direction, they may eventually meet again, even though the universe appears to be infinite on a local scale. The toroidal model offers exciting implications for the distribution of galaxies and cosmic background radiation, suggesting that certain patterns may recur due to the nature of the connectedness of space. The Mobius strip represents another interesting idea in world topology. It has a one-sided edge and is made by folding a strip of fabric in half and joining the ends together. If the world is structured like a Mobius strip, it will travel along different paths in space. To an observer traveling through this topology, it may seem as if he or she is returning to the beginning and seeing a change in perspective of place. This phenomenon raises interesting questions about the orientation of planetary structures and the possibility of unusual phenomena. Other proposed forms of the universe include the Klein bottle, which is a more complex structure that also has undirected properties, and higher dimensional analogues, such as the Calabi-Yau manifolds of string theory. Each of these shapes presents unique challenges and opportunities for modeling and understanding cosmic dynamics, influencing how we think about the overall coherence, history, and evolution of the universe. Studying these varied shapes allows scientists to expand their understanding of the universe beyond the conventional framework, potentially opening up insights into its ultimate destiny and the underlying principles that govern cosmic phenomena. As observational techniques and data analysis improve, researchers continue to explore these fascinating ideas, hoping to uncover the intricacies of the universe and the influence of its shape on our understanding of reality. The topology of the universe significantly influences what may exist beyond our observable boundaries, shaping the coherence and structure of space-time itself. Depending on the particular geometric configuration, the implications for unobservable regions can vary greatly, leading to several intriguing possibilities about the nature of the universe beyond what we can see. If the universe has a compact topology such as a torus, this allows the universe to wrap around itself. In such a scenario, this means that distant regions of space may be connected in ways that defy our normal understanding. For example, if you walk far enough in one direction, you will eventually return to your original location, as if you were traveling on a closed surface. This topology may mean that regions beyond the observable boundaries may contain copies or small variations of what exists within the observable universe, potentially leading to repetition of structures or phenomena. In contrast, if the universe has a more complex topology, such as a Mobius strip or a Klein bottle. The special non-orientable properties of these shapes may indicate an unusual space-time arrangement without traditional boundaries. This can lead to the existence of regions outside the observable universe that maintain continuity but exhibit different physical realities. In this case, traveling certain paths can lead to unexpected transformations of perspective or dimensionality, raising questions about the nature of time, space, and existence beyond our observations. The implications of space topology extend to the realm of the multiverse as well. If different regions of spacetime can have different topological characteristics, this could lead to the formation of completely separate universes, each governed by its own physical laws. In this context, the structure of our universe could exist alongside many other universes, potentially giving rise to a vast and complex multiverse. Observational evidence for the existence of such structures may be shown by anomalies or patterns in the cosmic microwave background radiation or in the distribution of galaxies. Ultimately, the topology of the universe serves as a lens that allows us to envision possibilities beyond our observable boundaries. It encourages us to explore radical ideas about the nature of existence, the interconnectedness of realities, and the very fabric of spacetime itself. As research in cosmology advances, a better understanding of cosmic topology may reveal a deeper understanding of the structure of the universe and the existence of yet unobserved worlds. Observational evidence supporting various theories of cosmic topology is still being developed, but scientists are already using various methods to evaluate cosmic structures and their implications. Although definitive evidence for the existence of specific topologies has not yet been found, several lines of research provide intriguing hints that may point to non-trivial cosmic shapes. One of the primary ways to investigate cosmic topology lies in analyzing the cosmic microwave background radiation. The faint afterglow of the Big Bang contains valuable information about the early universe and its geometry. By studying temperature fluctuations and patterns in the cosmic microwave background, researchers can look for anomalies or correlations that may indicate non-trivial topology. For example, if the universe has a compact torus-like topology, certain patterns may recur due to the closed nature of the universe. Specific analyses, such as looking for coincidence circles or anomalies in the temperature distribution, may indicate that the universe wraps around itself in certain ways. Another approach involves studying the large-scale structure of galaxies and galaxy clusters. If the universe has a unique topological configuration, researchers may observe unusual galaxy distribution patterns or features in the voids between galaxies. By mapping the location of galaxies over vast distances and analyzing their distribution, scientists can look for features that deviate from the typical predictions of a simple flat or open universe. If, however, certain structures exhibit repeating patterns or unexpected alignment, this may hint at a more complex cosmic topology. In addition, gravitational lensing provides another way to detect potential non-trivial topologies. Lensing occurs when massive objects such as galaxies or galaxy clusters bend light from more distant sources, creating multiple images or distorted views. By analyzing the lensing effects and locations of these images, researchers can look for evidence of unusual spatial configurations that may indicate a complex topology. Although conclusive evidence for the existence of specific cosmic topologies has not yet emerged, these lines of research indicate that we are on the cusp of expanding our understanding of the structure of the universe. Future advances in observational techniques, improved computational models, and larger datasets may lead to crucial discoveries that will help elucidate. This challenges our traditional notions of edges or boundaries and suggests imaginary scenarios of how space might be connected. For example, there may be regions of the universe that are out of sight, yet part of a larger underlying structure. Moreover, non-trivial cosmic topologies may have profound implications for the fundamental nature of reality itself. If our universe is part of a larger topology, this raises the question of whether what we perceive as independent galaxies are simply sections of a larger cosmic tapestry. This interconnectedness could also affect the propagation of light and gravitational waves, possibly allowing us to see traces of distant regions that would otherwise be inaccessible. Measurements from large-scale space probes may reveal patterns indicative of more complex structure and stimulate interest in the cosmological phenomena of the universe. Reflecting on these ideas will change our understanding of the boundaries of the world and encourage new insights into the nature of the world and the universe. Understanding how the universe is connected in unexpected ways opens up new ways of thinking about the universe, the origin of cosmic structures, and ultimately our place in this larger universe and connectivity.